In this video, I'm going to show you how to calculate the energy of a phase change. So how much energy do we need to put into a system to make the phase change, or how much energy do we get out of a system when there is a phase change? So what we're going to look at first is a heating curve for water, and this is very specific for water. It's not for any other substance. Other substances have similar looking heating curves, but they will have different values associated with them. So keep in mind, this is all the information for water. Now let's just say we have water at negative 25 degrees Celsius. Well, we all know that it's not called water when it's at negative 25 degrees Celsius. It's called ice, and ice is a solid. Now, you may remember that solids have fixed shapes. The particles are really close together. They're vibrating back and forth, and they're sort of in a pattern. Now, water doesn't necessarily form this pattern. Water particles don't necessarily form this pattern, but they do form a pattern, and they are in some sort of pattern orientation. So we have ice, and if we heat that ice, eventually we're going to get to a point, and that point is 0 degrees Celsius. That happens to be the freezing point or melting point of water or of ice. So we heat ice until we get to that 0 degrees Celsius. So if we continue to add energy to this ice, you might think that it melts. But it doesn't initially melt. What happens is first, that ice heats up to its melting point. So if we're going to calculate how much energy it requires to heat that ice up to its melting point, we need that mc delta T equation. Now the specific heat capacity for ice is 2.010 joules per gram degrees Celsius. Now, once we have that ice up to 0 degrees Celsius, we can continue adding energy, but the temperature won't change. And that's why the line there is flat. The temperature is not changing. So where is all that energy going? Well, it's going towards a phase change. It's going towards melting that ice. So if we continue to put energy into that ice will melt and turn into water. Now, if we take energy out of water, it freezes. So the reverse is freezing. So putting energy in is melting. Now, there's a different equation for calculating how much energy it takes to melt that ice, and that is the Q is equal to the delta heat of fusion times the mass. And the delta heat of fusion for ice, or for water, for H2O, is 334 joules per gram. Notice there's no degrees Celsius in here because the temperature is not changing. Now, once all of that ice is melted, then we can begin a temperature change. So we continue to put energy into that melted ice. Eventually, all of it will turn to water, and the water can now begin to absorb that heat and have a temperature change. Now, reminder, water is a liquid, and liquid particles are pretty close together, but they're not in a specific pattern. They're free-flowing, and they can move past each other. So as we're heating this water, we can heat it and heat it and heat it, put more energy in, and eventually we're going to get to a point. And that point for water is 100 degrees Celsius. And 100 degrees Celsius happens to be the boiling point of water. So we can calculate how much energy we put into heating water. We've done this before. mc delta T, the C is 4.184 joules per gram degrees Celsius. Notice how we have a degree Celsius because now we have a temperature change. So the temperature is changing, and it's going to change until it gets to that point, and then we can continue putting heat in, and it won't change temperature because what's happening is we have another phase change. And that phase change is the phase change between a liquid and a gas. That's called vaporization. So all that energy that we put in is not going towards increasing the temperature, it's going towards changing the phase. And if we take energy out of that gas, we condense it and it turns into a liquid. So the reverse is condensation. So a new equation for this, the calculation for this phase change, and it's the delta heat of vaporization times the mass. And the heat of vaporization for water, for H2O, is 2,257 joules per gram. Notice we don't have a degree Celsius in there because the temperature is not changing, just the phase. So now we have water in gas form, which we call steam. Steam is water in gas form. And just a reminder, gases have particles that are very far apart. They're very high in energy, and they're moving really, really, really fast. There's no fixed shape, there's no fixed volume. They take the volume of their container. Now what we can do is we can heat this steam. We're going to heat it to 25 degrees Celsius, heat it to 125 degrees Celsius. We could heat it a lot hotter than that, but just for the purposes of this, we're going to go up to 125 degrees Celsius. So the energy it takes to heat that steam, we're going to go back to the equation that we are familiar with, the MC delta T. The specific heat capacity of steam is 2.010 joules per gram degree Celsius. So it does depend on how much you're heating that steam. How many degrees Celsius are we heating that steam? All of these processes put together, we add all of the processes together and we can get the total amount of energy that it would take to take a piece of ice at negative 25 degrees Celsius all the way to some steam at 125 degrees Celsius. So let's do some practice. How much energy is needed to completely convert 350 milliliters of water at 45 degrees Celsius to steam? And we're completely converting it. What I like to do is I like to start out with a little tiny sketch of an energy diagram or a heat curve for whatever substance I'm talking about. It's always going to be water for the purposes of this class. So if I start with water at 45 degrees Celsius, that's the water right there, and I need to heat that water to 100 degrees Celsius. So that's the first step in this. And once I heat it to 100 degrees Celsius, then I need to convert all of it to steam. So there's two steps in this process. There's the heating of the water, and then there's the conversion of all of it to steam. So the first step is and I'm going to just label this here. So the first step is heating water. So how much energy does it take to heat that water? So we're going to use our MC delta T because we're heating it. There's a temperature change. So the mass of the water is 350 grams because of that density there. And the C, or the specific heat capacity of water, is 4.184 joules per gram degree Celsius. And now I'm heating it from 45 up to 100. That's a temperature change of 55 degrees Celsius. So if I type all of this into my calculator and I multiply these numbers together, I get 80,542 joules. I will round for my significant figures at the end. So I have 80,542 joules it takes just to heat that water. The next step in this is to vaporize the water. I'm completely converting all of it to steam. So I need the delta heat of, actually that's not fusion, delta heat of vaporization. And we're gonna multiply that by the mass. So the heat of vaporization for water is really large. It's 2,257 joules per gram. It takes a lot of energy to get that water to turn into steam. And I have 350 grams here. So if I multiply the two numbers together, I get 789,950 joules. That's a lot of energy it takes to convert that water to steam. Now what I'm going to do here is I'm going to add those two energies together. When I add them together, I get 870,492 joules. I'm going to convert this to two significant figures here. I get 870,000 joules, and then I'm going to convert it to kilojoules just because 870,000 is a pretty big number. So I get 870 kilojoules of energy it takes to completely convert this amount of water at 45 degrees Celsius all the way to steam. Let's try another practice problem. This one's a little bit trickier. We have a 12.0 gram ice cube, and it's at -8 degrees Celsius. It's placed into 500 grams of water at 27 degrees Celsius. What we want to do is we want to calculate the final temperature of the water once the ice is completely melted. And we're going to assume the water gives that ice all the energy that it needs to completely melt. So I start out with my sketch here, my phase, my heating curve for water. And it's going to start at -8 degrees Celsius. And we're going to heat that ice from -8 degrees Celsius up to 0 degrees Celsius. That's the first step, is we need to heat that ice to 0 degrees Celsius. And then I'm going to melt the ice. So I'm going to figure out how much energy it takes to heat the ice and then to melt the ice. So first we'll start with the energy it takes to heat the ice. This is our MC delta T because there is a temperature change taking place. So our mass is 12.0 grams. Our C for ice is 2.010 joules per gram degree Celsius, and we're heating it from -8 to 0. So the temperature change is 8 degrees Celsius. So that's step 1, and I'm going to multiply all of that out and get a number. Remember, your joules or your Celsius and your grams cancel out, leaving you with joules. So I have 193 joules for this process. The second step is the amount of energy it takes to melt the ice. So I need to know my heat of fusion, and that is the delta H fusion, which is 334 joules per gram. Remember, there's no temperature change taking place, so I have no degrees Celsius in that unit, and I have 12 grams of the ice that needs to melt. So this is a total of 4,008 joules. I'm going to add these two numbers together, and I get 4,008 plus 193. I get 4,201 joules. Now this is the amount of energy that the ice cube needed. So it's that amount of energy is coming from the water, that 500 grams of water. So what we want to know is we want to know the change in temperature of the water. And of course, if you put ice in water, the temperature is going to go down. So we should be able to predict that we're going to have a lower temperature. So we start with 27 degrees. We're going to end with something lower than that because we put an ice cube in it. So the amount of energy that the water lost was 4,201 joules. Now the mass of that water is 500 grams. The C, or the specific heat capacity for water, is 4.184 joules per gram degree Celsius. And we don't know the change in temperature of the water, but we do know that, we don't know the final, but we do know that the initial temperature of the water was 27 degrees Celsius. So this is our equation. This is how we're setting this up. Now what I'm going to do is I'm going to divide both sides by 500, and then I'm going to divide both sides by 4.184. And when I do that, I get a -2 degrees Celsius, everything else cancels out, equals the final temperature minus 27 degrees Celsius. So if I'm figuring out, if I'm solving for the final temperature, what I'm going to get is, if I add 27 degrees Celsius to both sides, what I'm going to get is 25 degrees Celsius for my final temperature. And that makes complete sense because I have a large amount of water and I put a tiny little ice cube in it, and that ice cube melted. What that's going to do is that it's going to bring that water temperature down just a little bit because I have a lot of water and just a tiny little ice cube, so it changes that temperature just a tiny little bit to melt that ice.